Yeah, hello everyone. Very good evening. Yeah, so 1 or 2 days, if you don't give attendance, that's fine. Okay. So if you have been giving the attendance, so all these days, so that's okay. No problem. Mukesh, can you stop sharing the screen? All right. So as I mentioned, yeah, 1 or 2 days, if you, yeah. So if you have not given the attendance, that's okay. Okay. Yeah. So still you will be able to get the certificates. That's fine. All right. So let us get started. So yesterday we have discussed about feature engineering, so as well as model validation techniques, and also we have discussed about the accuracy methods. So today we are going to discuss about the another tree based methods such as XGBoost and LGBM. Right. So XGBoost and LGBM, these two methods are very popular methods. And also, they are giving these two methods are giving us a very good accuracy in comparison to any other models. Mostly the conventional models when it comes to like our C5.0 or CART or SVM in most of the cases, right? So because this is again the ensemble methods, these are the ensemble methods we are going to discuss. So let us discuss what are the internal mechanisms of this XGBoost as well as LGBM. So extreme gradient boosting algorithm, XGBoost. So it was developed as a research project. So at the University of Washington. And these are the guys, as part of their PhD thesis. So they have developed this algorithm. And after that, they have presented this paper in 2016 in one of the machine learning conferences. And from then, actually, yeah, so this methodology has got very popular. So in the data science community. So because it is giving us the robust, the algorithm as well as the good accuracy on a given data set when it compares to other algorithms. And this XGBM, right? So this is the ensemble methods, and mostly, so this will be used the CART, classification regression algorithms, internally. Okay, right. Now let us think from the supervised learning, the algorithms perspective. So how a supervised machine learning algorithm can be represented in a mathematical way. So we can represent, okay, so yi hat is equal to, so sigma, so theta j, so basically this is the hyperparameters you can say, and xj. Theta j is basically parameters. So like beta naught, beta 2, beta 3, like that. So xj is the independent variables. And generally we'll mention like this. If you think of a linear regression equation, so we'll represent that linear regression equation like this. Okay. Now, any objective function. So when it comes to the supervised machine learning, so the objective function is we want to minimize the error. So what is the error? So error, so we have discussed that. So sigma, okay, so yi minus yi hat square. So this is nothing but the mean squared error. So for any given algorithm, so we want to minimize this. Okay, what do you mean by minimizing this quantity? So this is error quantity, right? We want to minimize this error quantity. Then how do you minimize this error quantity? So what is in our hands? See, yi, this is the actual data point from the data set. So this you cannot change. And what is there in our hand? Yi hat. So what is yi hat? So if you see, so yi hat, so how do you get this yi hat? Based on our regression equation. If you are talking about the simple linear regression equation, so beta naught beta 1 x. All right. And now, so beta naught beta 1 x. So these are all the parameters so that we can identify from the given data set. So if you can identify this beta naught beta 1 such a way that so this error is minimum, then these two parameters are the best parameters. This is what we want to minimize this quantity by identifying the best parameters of this beta naught beta 1. Now, so if you see any objective function, that objective function should comprises of training loss and regularization term. What is a regularization term? The regularization term prevents the overfitting of the model. So if you recall our discussion on the decision tree, or when we're discussing about the classification, we have discussed about the highly, okay, so these are the classes, let's say. So highly nonlinear model. So this is overfit model because this model is remembering the data points from the data set. This you can say is a overfit model. Okay. Yeah. Now, so when you use a term called regularization term, it makes sure that the model is not overfitting. In case of decision tree, we have applied a method called pruning. Okay, what is pruning? So pruning is a way to prevent the models or the decision trees to overfit the data. Okay? So that means any objective function will have two terms, should have two terms. One is the loss function, the other one is the regularization term, that is omega. And what is the loss function? The loss function is this, whatever the error that we are talking about. So this is the loss function. And this term, the regulation term also should be low. So when you say the objective function, so should have the low value. Okay? So this should be low, and regulation term also decent enough. When I say low, again, when we build a low regularized model, that means very low complex model, then that is not going to work for us. So when you build a model which is very low complex, then definitely your loss function will be very high. The error will be very high. That means the model is very weak model or so very low accurate model. Then what would be your error? Error will be definitely very high. That means so this would be very high. So meaning so we have to find out the a line basically, so that balances out so the complexity of the model as well as regularization of the model. A trade-off between the loss function as well as the regularization of the model. So the objective function, so as we discussed, comprises of these two methods, two the terms loss function as well as regularization term. Now coming to the loss function, so this is what actually we discussed. So here L of theta is nothing but the mean squared error. So this is one of uh, the loss function that we can use. Okay, so the mean squared error. But do we have only one the loss function like this mean squared error? No, we have many loss functions that we have. Let me show you here. Yeah. Especially in this XGBM, we are going to use for regression. We'll use this the mean squared error here. For binary classification, okay, where we have the two class problem, yes or no, we would use this log loss. For a multi-class classification, we'll use m log loss. Okay. So these are the different the loss functions we are going to use as part of this the XGBM. Okay, so this is, you can think of L of theta based on the number of classes or what kind of problem that we are trying to solve. So coming to regularization term. So this is my data set. Okay. So this is observed data, that means real data. Okay. So when you build a model, so which is very high complex model. When you say high complex model, where you see, so the number of splits are very high, too many splits. So what is too many splits? Like this. So those are too many splits for a given data set. So in this case, you can say the regulation value is very high. The term regulation or complexity of the model is very high. That means, so this model is overfitting the data, and this model is not going to work out. So in the production environment, and this one, so here the complexity is not that high, but the loss is very high here. The loss L of theta, because the split is, so the split that has happened is going to give us a very high error, because this is what actually you can think of error, right? Though the complexity is not that high, but the loss is very high for this model. But what is the right model? The right model is with a reasonable complexity. That means, so here we have a reasonable complexity. The error is also very low here. The loss L of theta is low, and complexity, the omega, is also a reasonable complex model. That means the model, so is rightly split, and almost, so the error is almost zero here, because all the data points are so on this line. And this is a right model. That means we have to balance out the loss as well as the complexity of a model. Okay, so that's how, so we have to build. Then, so what is so important here? The important thing here is, so if you use only the loss function to identify the best parameters, see, when we build a model, so y is equal to beta naught plus beta 1 x. So this is what actually linear regression equation is. So if you focus only on the error, okay, so yi minus yi hat, if you focus only on this error, probably you might get the best one, but we do not know whether that model is overfit or not. So which one gives us the idea of the overfit? The regularization term. So when you add a regularization term for this, so a regulation term for this, then so this term so would prevent that model to overfit the data. Okay, so that means every model, every algorithm should have, yes, so the loss function plus regulation term to the objective function. So then we can say that, okay, so that model is a good model, balanced model. Okay, now coming to our XGBoost. XGBoost uses CART, classification and regression trees. CART. Right? So we have seen this CART already. This can be used for the regression problems as well as the classification problems. Okay. Let us say, for example, we have a classification problem whether someone would like computer games or not. Okay, so it's a classification problem. The input data is age, gender, and occupation. These are the different characteristics of the data point that we have here. And we have built a tree here, and so you can imagine that the data points are going through this filter one by one. Okay, through this filter one by one. Now, so here the first node is age is less than 15. Yes, no. So if it is male, again here it is yes, then no. Then if when you send these data points, so here we can see a kid here, right? So it is less than 15, a male, and the scores are so defined. So we'll discuss how do we compute the scores for each of these leaves. So each leaf will associate a score here, and whatever the data point that comes here, so we would use these scores for the prediction purpose. Now here you can see, so the data point came here, and again one more data point here. Here we have 3 data points. Now like this, so in CART we are going to build multiple trees. So there's a tree 1 and tree 2. That is where actually we can say this is ensemble model. Now if you want to find out whether this person, this kid, or this data point is going to like the the computer games or not, what we do, across all the trees, I would compute the scores and add all the scores. So for this data point, okay, so here we have plus 2, and here we have this data point plus 0.9. This is 2.9. And here we have, for this data point, you can see -1, and here we have negative minus, 0.9, and this minus 1.9, and here 2.9. So based on the score, we can interpret that, okay, so this kid is going to like the video games, and so this elderly person is not going to like the video games. That means, so we are going to build multiple decision trees or carts, and based on the score on the leaves, we are going to add all the scores based on the which data point is going to which leaf. We'll accumulate all the scores, and then based on that score, whatever the score that we have got, we will interpret. So that's how the ensemble method in the cart we are going to use. How do we mathematically represent these things? So if you see here, so one model, okay, I can say f of, okay, x. So this is my hypothesis. That means there is the mapping between the input variables to output variable. This is one model I can say. When you're building k models, I can say, so fk, okay, xi, so k equal to 1 to n. That means, so we are going to build k models and accumulate or sum up all the models scores. And that is how actually we can represent the ensemble methods. And the objective function is basically, we are going to build, okay, so k models or k number of trees, or all these models, find out the loss. How do you find out the loss? Yi hat. Okay. So that means the difference between the actual value versus the predicted value, that is a loss, and compute that loss over n number of data points across all the trees. And then this is my regularization term. This regularization term, what it controls is, it controls the number of trees that we are going to build. K equal to 1 to k omega fk means, so how many number of trees we are going to build. That means if you are going to build too many trees, that means you are trying to overfit the data. The number of trees, if you are going to build more and more, so these trees would try to remember the data points. So that is the sign of complexity, higher complexity, or overfit of the model. Now, so while this term reduces the error, and this term controls the complexity of the model. Yep. So this is what actually we are going to use, and let us see how we can apply this for the XGBM algorithm. Right, so this is objective function. Now, so how are we going to use all these decision trees? How are we going to build these decision trees? We said that, so tree 1, okay, tree 2, like this we are going to build, right? Then what is a strategy? So how are we going to use all of these trees in the ensemble model? What are we going to do is, first you build the model, first model, then optimize this decision tree, whatever the model that you have built. Okay, so this is the first model, and using my objective function, so wherein we have L of theta, and then so this omega, okay, a regularization term, and use this method and optimize this decision tree. When it's optimization of the decision tree, so we should make sure that this is giving us the enough accuracy, good decent accuracy, and also this not overfit the data. Okay. First build a model, a decision tree, and optimize this decision tree. Then go for the next decision tree. Then optimize that. Then go for the next decision trees. Like that, you build as many number of decision trees that you want. Then add them up one by one, one by one. Okay. So that is what actually we are going to follow. That this approach is called as additive training or additive model building approach. First, I would build a model f1 of xi, then go for the next model, then go for the next model, then add them up. This is what actually we'll see. So our trees, we are adding all these models that I can represent like this. So y of, or y hat of t minus 1 plus ft of xi. So this is what actually, so when you we will get when you add multiple trees. Now we will use, so this formula will replace in the last function here. Okay. Our last objective function is, so this last function plays the regularization term. And this last function we have yi, so hat t. And we are going to replace with this definition of additive training. Replace this. So yi hat plus ft of xi, then our regulation term as it is. Right. Now, so let us focus on this. Now we are going to build a error function out of this. The error function that we are going to use is mean squared error, or MSE. Okay, MSE we are going to use. So what is MSE? MSE, as we discussed, yi minus yi hat square. And what is the last function that we discussed? So that is what here, and square of this. And this term we are going to approximate using a Taylor series, Taylor expansion series. And this term we are going to approximate. Okay, so that Taylor series approximation for this is here. So we have first order derivative of the last function, that is gi, second order derivative, the partial derivative of the last function, that is hi, and then our regulation term as it is. So gi is a partial derivative of last function. This is a first order partial derivative. So hi is a second order partial derivative of last function. Right? So then when you, after applying some mathematical process, so then you'll get this. Right? The final, the objective function for this XGBM is this: first order derivative of the last function, then your decision tree function, then second order, then your decision tree function square, then my regulation term. So this is what the objective function for the XGBM. Now coming to the regularization term, how do you define this term? So this we have defined, and how do you define this regularization term? Let us discuss about that. So ft of x, okay. So how do you define a tree? The definition of the tree is basically, so wq of x. The w is nothing but the scores on the decision tree. We have seen, right, the scores. Okay. The scores, whatever the scores that we have here, we are going to see how do you compute that. For each node, we'll have a scores like +2 or 1.9 like this. So the W is nothing but the vectors of scores in a tree. And so here the Q of x, what it does is, this is a function. So it looks after what data point or which data point should go to which leaf node. So that will be taken care by the Q of x. And here this T, the T is basically number of leaves in a decision tree. So how many number of leaves are there? So that is what the T here. You can think of T as a regularization parameter, how to control the regulation parameter. Because if you have more number of leaves, that means the depth of the decision tree is very high. Then you can say that is very high complex model. Okay? That means using T, I can control the regularization of the decision tree. So that is where we are going to use this T in our regularization parameter. This is my regularization term. Gamma T. T is what? The T is nothing but the number of leaves that we have in the decision tree. And also W. So W is basically the scores on the leaves, right? Or all the leaves. So WJ square means this T, J equal to 1 to T means over all these leaves, sum it up the scores, and the score also we are going to use as a regulation parameter. So if both are low, when it's a low, a decent enough. So even if it is very low also, that is not good because the model is underlearned, right? So in this case, the model is underlearned and it controls a decent enough, the complexity should be there in a decision tree. And again, so when you say decent enough, it is not the very low complex or very high complex. So we should have a trade-off between low complex and high complex. So right set of complexity we should build. So that will be taken care by this omega. That is a regulation term. Right. Now the tree building methodology. So how the decision tree would be built? So what is the structure of the decision tree here? Okay. The core concepts are same. So any decision tree that you take, core concepts are same. Internal nodes. So how the internal nodes would get split? Each internal node split the flow of the data points by one of the features. Okay, so these are all the nodes, okay, are splitting, and the data would flow through these nodes based on the criteria that we have mentioned. Okay, and the condition, what are the condition that we mentioned, based on that the data gets flows into these nodes. And the leaves data points reach to a leaf will be assigned a weight. We are going to compute weight for this leaf, for all of these leaves. Okay, and what are the data point that goes to this leaf, we will assign certain weights like this, and this weight will use as a prediction. Okay, these weight, whatever the weights that we have here, so these weights we are going to use as a predictions, right. Then how do you compute that leaf score? Whatever we are talking about, this leaf scores. So here we have a W1, okay, W2. These are the vectors of scores. So how do you compute these leaf scores? The leaf scores we are going to compute using this formula. So that is for a particular node or for particular leaf, we are going to use this. So GI. So GI is basically the first order derivative, partial derivative of the last function. So HI is the second order partial derivative of the last function plus lambda. Lambda is a regularization parameter again. And using this, we are going to compute the weights. So these weights would be assigned for each of these leaves. Right. Now coming to the best split. How do you define the best split point in case of the XGBM? Okay. So how do you define this best split? So here we are going to use the gain basically. Okay, the gain or information gain. So here we have a different methodology to compute this information gain here. So what we do is we'll compute the leaf scores. Let us say, so here, let's say for example, this is a node here. I'll compute the gain for this. Okay, again using the same formula, the leaf scores. So if I divide this node into the small or children's like this, so left side and right side. So I can compute the gain for this left side. I can compute the gain for this right side. Then what I would do is, so I'll add this left and right, then subtract from this. If the result is positive, then I can go ahead and split it. Otherwise, I cannot go ahead and split it because the information gain is negative. For example, see here we have a left side gain and this is a right side gain. Sum these, subtract from the main node here, the parent node. If this is a positive, then we can go ahead and split that node so that we'll have the more homogeneous regions. If this is negative, okay, if this is negative, this the term is a negative, then so we are not going to form any more homogeneous regions. So that is how actually the best split would be identified, whether to go ahead and split that node further into children, or so just leave that node as a leaf node, as a final node. Based on this gain, we are going to compute that. Right. So finally, So how do we, build a decision tree, and how do we use that scores for the prediction purpose? Let us, for example, I have a decision tree like this. So this decision tree, so the age, male, and some other factors we have used as a criteria. What we do is, for each of the data point, we are going to compute the gradients, the first order partial derivatives and second order partial derivatives. And the q of x, so this is a function that takes care of which data point should go to the which leaf node. So based on the criteria that we have mentioned here. So first data point. So here first data point is a kid less than 15 years of age and male. So this data point, first data point, should travel to this side. So I1, the index is first data point. G1 is equal to the first partial derivative, H1 second order partial derivative of the last function, and I'll use these statistics. I'll compute objective function. Okay, so then again here also, if it is no, so the second, not second data point, the fourth data point, so that reaches to this node, and I'll have this. And here we have three data points. So these three data points, again, first order, second order partial derivatives I'll compute. Now G3 and H3. I'll take all of these values, compute my objective function, and this has to be optimized. When it's optimized, so this should not be a highly complex model, and at the same time, this should not be a low complex model. The trade-off should be maintained. Then I can say this decision tree is optimized. Then go for next decision tree. Then go for next decision tree. Apply these methods. Make sure that the decision tree is optimized. Okay, the smaller score, the better the structure, the decision tree structure is. So once you have the different decision trees, then we'll use those trees for the prediction purpose. Okay, so that's how we are going to use this XGBM, and will use for the prediction. In case of classification or in case of regression, also we can use this. Yeah. So what are the advantages, okay, or enhancements of this XGBM model? So this is a parallelization. So the XGBM or XGBoost follows a process of sequential tree building. So as you see here, the trees are getting built one by one after the other, right? So first tree 1 will be built. Then once we optimize this, then we'll go for the tree 2, then optimize this tree 3. So that means there's a sequential building of the decision trees. But while so it follows sequential approach, it also implements parallelization of the implement, a parallelization of the decision trees. Probably what it does is, so it builds partially this tree 1, and again it goes for the tree 2 or tree 3. Parallelly, it also builds, and then it optimizes tree 1, then go for tree 2 or tree 3. Okay, so that way the algorithm running, the time to execute over all the data points, so would be optimized. It doesn't take much time in comparison to other sequential model building methodologies. Okay, so that is one of the system optimization. And tree pruning. So tree pruning, so we can use max underscore depth is a parameter, so for to control the complexity of the model. Okay. And the other one is algorithmic enhancements, a regularization. So it penalizes more complex models. So it has inbuilt the mechanism to punish the decision trees which are highly complex. It uses lasso and ridge regressions or regulation methods to control the overfit of the models. And sparsity awareness. The sparsity is basically when you have the input data. Okay, when you have the input data, more number of zeros in the input data. 0, okay, 0, 0, 1, 5, 0. When you have more number of zeros in an input data set, that is called as sparse data set. That means most of the values are absent in a data set. So that's the data set is basically called as sparse data set. And the XGBM so identifies, so what is the sparsity in the data set, and so it doesn't include, okay, if at all the sparsity is very high in a feature or in a row, so it tries to ignore or discard that row so that it speeds up the calculations. And cross validation. So the XGBM has an inbuilt methodology for the cross validation. That means you don't have to explicitly run this cross validation on this algorithm. Whatever the validation method that you apply. Okay, so inbuilt as an inbuilt in the algorithm, it applies cross validation on the data set and gives us the accuracy. Whatever the train test split method that you use, right, and that itself is a cross validation for the XGBM. So these are the some of the enhancements that have been made in the algorithm. Yeah. Right. So that is the XGBM. Now coming to LGBM. So LGBM is a light gradient boosting machine. So this is from Microsoft. So LGBM uses a novel technique called gradient based one-sided sampling. Okay. So that is GAUS. So gradient based one-sided sampling to filter out the data instances for finding out the best split value. Meaning, so what data to be used to build the decision tree? Okay. Out of the data set that we have, should we give equal importance for all the data points for building of the decision tree? Or should we have a mechanism to identify the best data points, and those data points would be given prioritize or the higher priority for tree building? Okay. So based on the high priority or what kind of data points should be given high priority while building the decision tree, so that is what the GAS all about is. That means it is a way of identifying or filtering data points or sampling the data points for the model building. So if you recall our the ensemble method AdaBoost, AdaBoost use excuse me, AdaBoost uses a methodology called weights, right? We have seen the other day how AdaBoost works. Like it gives all the data points a weights. Then the data points which are classifying wrongly would receive higher weights like this. And based on these higher weights, the next subsequent models would identify, hey, these data points have to be given higher priority. Now in this LGBM, this kinds of weight scheme is not available, but the idea is the same. Whatever the data points which are giving us more error, which are not getting classified correctly, those data points so would be given higher priority for the model building. But how these data points would be identified? So these are highly wrongly classified data points, and most of the time the data points are classifying wrongly. Those data points would be identified this method GAS, gradient based one side sampling. Let us see what is this gradient, the one side sampling. The gradient is slope, right? The gradient represents the slope of the loss function. The idea here is if the slope is more for a data point, if the gradient is more for a data point, that means so that data point has high error. Let us say data point 1. For this, if the gradient is more, then I can say that this data point has a high error. If a data point, the gradient is low, very low, that means the error is low for that data point. Based on that gradient high or low for a particular data points, we are going to prioritize these data points. For a particular data point, the gradient is very high. Then, so I'll sample the data point for the model building. If a particular data point gradient is very low, that means, so this data point is not going to be useful for me or for my algorithm to learn from the data point. Okay. So I'll not prioritize this data point. So likewise, I'll find out from all the data points, so which data points have high gradients, that means high error, those data points so would be selected for the model building. And while some of the data points from this low gradient we are going to take, it is not that only the high gradient data points would be given importance, but also we'll take some portion of the data point from this low gradient. For example, I have 500k rows, so 5 lakhs data points. Out of these 500k data points, 10,000 data points have higher gradient. Let's say, for example, this is this scenario, 500k data points. Out of this 500k data points, okay, 10,000 rows. So 10,000 rows so have higher gradients. So I'll take this 10,000 data points, okay, for model building. Okay, so this is the data preparation stage. You can think of data prep stage. So all these 10,000 data points I'll take into the data set, while the remaining this 490k, okay, 490k, out of which what I would do is I'll take 10% of the data, 10% of this data. What are these 490k? These are low gradient data points, and these are all very high gradient data points. The intuition here is, if a data point has higher error, so there is a high chance for the model to learn. The data point as doesn't have the much error, very easy to classify, very easy to predict, then from there model doesn't have much to learn actually. So that is based on that assumption. We are going to segregate the data points based on the error. So the data point is going to produce. And here, what is the total data set here? So 10,000 plus 49k, 10% of 490k. So total here we have 59k. So this is the data set we are going to use to build the model. This is one tree, one decision tree. So while building the second decision tree, again I'll take the 10,000 data points. So from the high gradient data points, and again randomly I'll sample 10% of this 490k. So here we'll have a different data set again. So using this different data set, I'm going to build a decision tree here again. So like that, we are going to build many decision trees by taking random sample of this data from the 490k and by keeping the 10k constant every time, and we'll build different decision trees. And these are all the ensemble. We will use all these trees in the ensemble method. Right. And here also we have certain enhancements in this LGBM also to speed up the learning process. So those enhancements are like this. So histogram based method. So what is this histogram based method? So while splitting a decision tree, so we have seen, right, when you split the decision tree, it has to go through each and every feature. Okay. So this is feature one, and here we have values, let's say 5, okay, 3, 2, 1, okay. So like this. Now, in order to identify the best split, right. So it has to split for every, yeah, so every value here, let's say for example, as we have seen, less than or equal to 5 and greater than 5. Okay, so then we'll check that the accuracy and all those things. Then I'll go for next split. Let's say for example here, then here, then here. So like that, we have to check for each and every split. That takes a lot of time. Now here, to speed up the process, so what has been done here is histogram based approach has been introduced. As part of this, so what we do is we will sort this column. After sorting this column, we will categorize like this. So all the values which are less than certain value, less than 9, I'll mark them as 1, 1, 1. All the values which are above, will mark them as 2, 2, 2, like this. Now, instead of these many splits, okay, now we are going to mark them as 1, 1, 1, and this is 2. Now, how many splits we have to do now? Only one split. So one is less than or equal to 1, the other one is greater than 1. I'll check here. So I don't have to split this, don't have to check for all the values in this feature. I'll have to check only for these values. So less than or equal to 1 and greater than 1. Right? So this is basically called as histogram based method or grouping method based on the values. So we are going to categorize these values into 1 and these values into 2, then next subsequent values into 3, 4, 5, like that. We are reducing the levels. We are doing what we are doing here is we are reducing the levels, and we don't have to check many number of values here. Okay. Yeah. So that eventually speed up the learning process. And also it ignores the sparse inputs as we discussed in the XGBM. So the LGBM also ignores the sparse values. So if at all in any column, in any feature, the values are more values are 0, then this algorithm would ignore. Anyway, so if you have more number of values are 0, so from that feature, the algorithm doesn't learn anything new, right? Yeah. So the other enhancement that has been done in this LGBM is feature bundling. Okay, what is a feature bundling? Let us say, for example, I have feature 1 and feature 2. The feature 1, let's say, for example, I have a value 0 here, this is 5. So this 3, this 0, 10, 0, 0, 1. Okay, and 1, let's say, yeah, 0. So like that, we have features. If you observe this, the pattern, both these features, the 0 never occurs for a given data point. So this is data point 1, 2, 3, 4, 5. For a given data point, For both features, the 0 doesn't occur, and both features never have a value more than 0 at a given data point. So if you see here, data point 1, if feature 1 is 0, the feature 2 will have some value. Feature 1 has some value, feature 2 has 0. That means, so at any given point of time, at any given data point, so one of these feature is becoming 0, and the other feature will have at least some value, 1 or 2 or more than 0. Now what we can do is, I can combine these two features, I can bundle them. So f1 plus f2. Okay, so this 5, this is 3, this is 10, this is 1 and 1. You see? So instead of these two features, I'll use only one feature, and I'll keep track of. So which one is a 0 at what data point, and which one has that value. Now here we are reducing the dimensionality here. And this is called as feature bundling. Okay? So this will be identified automatically wherever it is possible in the data set, and it applies this feature bundling so that the dimensionality would be reduced. And the other difference or other enhancement, yeah. So the other enhancement that has been introduced here is a light GBM. So how the decision tree goes. There are two kinds of the tree building methodologies. One is leaf-wise algorithm. The other one is level-wise algorithm. What is a level-wise algorithm? The level-wise, the tree growing is like this. First, we'll have a root node, then left side node, then right side node. This is one level completed. Then split this left side node and complete this left side and right side. Then go to this node. Then second level is completed. So like that, at every level, just make sure that all the nodes are created, all the leaves are created. Then go to the again to split the next level leaves. So this is basically called as level wise growth. When it comes to leaf wise, first what it does is, okay, then completely build this left side. You see, so this leaf, okay, this leaf is actually growing here. Okay, once this leaf grows completely, then move to this, then move to this, then move to this. So like that, so this leaf wise growth would be, has been implemented in this LGBM. Okay, so this is another difference in comparison to the other decision trees, the level wise and leaf wise growth. Okay, there's a question, gradient could be positive or negative, right? Okay, increasing order. Right, so high means positive, yeah. See, when you see, for example, the gradient, so if you talk about the squared loss function, the gradient always gives us the direction, the steepest ascent. Okay, if I'm here, if you want to find out, so where should I go, which direction I should go, so I can apply the gradient at this. So after drawing a tangent here, so at this place, the gradient would give us the steepest ascent direction, for example. Then I have to go to the exactly opposite direction. Okay, so this direction I should go. Okay, so this gradient, whatever gradient that you get, okay, the positive gradient that you get, so if it is very high value, then that means that data point has high amount of error. Okay, yeah, when you apply the gradient on the last function, you would get the steepest ascent, then you will go in the exactly opposite direction to that steepest ascent, then you will get the steepest descent. So that is a gradient descent algorithm. Yeah. Right. Now let me show you how to implement this in Python, the XGBM and LGBM. Just give me a minute. Right. So this is Google Colab. Okay. So if you're not aware of this, this is Google's initiative, and this one they have given us free. In the Google cloud platform, you can execute the Python engine like this, and they're giving us a very good the configuration machine, like so almost 13 GB RAM, and you can see the tooltip here, and the disk space is 107 hard disk. That means you can save that much amount of data, and also you can use this RAM size of 13 GB. Okay, so which is definitely higher than our normal laptops. Generally, will have 8 GB RAM, right? And if you want to do some good analysis, which requires a good configuration, and you can use this Google Colab. You can just type in Google Collaboratory. You can see this collab.research, and which is a cloud-based Python engine. Let me load the data here. So here you can, yeah. So this is a command to install the packages XGBoost, LightGBM, load the packages, then load the dataset. Right. And then use this train test split method, divide the train and test dataset. So instantiate this XGB classifier and build the model. Model.fit X train, Y train. Right. So these are we can predict it. So once you build the model, then we can use predict command, and you can apply the test dataset on the model. Okay. So once you get these, yeah, predicted values, then we can generate the classes yes or no. Then let us find out the accuracy. So accuracy score, we are going to find, we are going to apply this confusion matrix. Y test is the actual data points, and the predictions are predictions made by the model. So the accuracy is 77.95. So if you want to see the predictions for each of the data points, so these are you can see. Right. So this is the first data point, the prediction, second data point, third data point, like that. So we have all the data points predictions. Right. Yeah. Then the next one is light GBM. Okay. Already we have loaded the data. Import the library here and convert the data set into the LGB data set. So the LGBM has a different data structure, and we have to convert our data set into the LGBM data structure. So that's what actually we are converting that into LGB data set. And these are all the hyperparameter tuning, like learning rate, just to identify the gradient. So how much the weights have to be updated every time, right? So that is what the learning rate here. So these are gradient boosting decision trees, the binary. So these are the complexity parameters, how you want to compute, how you want to control them. So 1500. Okay, let us try with the 150 trees. Okay, so here the 150 is nothing but 150 trees we are building. Then predict on the test data set, accuracy. Yeah, 70% is accuracy from this LGBM. Now let us increase the number of trees. For example, we have mentioned, okay, 150, right? So let me go for 500. Let us see how much is accuracy. Right. So from 150 to 500, the accuracy has been increased to 78%. Let us increase further. Okay. Let us see if you have any accuracy further. Yeah. So that is a max that we are getting 78%. So with this number of trees, right? So that's how we can see. And also these are the hyperparameters. We can also change. We can check, by changing these hyperparameters, and probably, so here minimum data points I mentioned 50. So this is one of the complex parameter. Let me mention 20 here. Minimum number of leaves. Okay, let me change it to okay, 6. The maximum depth, okay, let us go for 20. So just be relaxed the complexity, and let us see how much accuracy you'll get it. Yeah, max is 78 is the accuracy, even if you relax the complexity further. Okay. Yeah, so these are, we can build the model and you can fine tune the model. Okay, so let us take a break now. Okay, now a short break, 5 minutes break. Then, so after that, we will discuss about the k nearest neighbor model. Right? It's 603, and we will resume our discussion at 608. Okay, so the next algorithm we are going to discuss is k nearest neighbors or KNN. Okay, KNN, right? So if you see the value k, so if you recall the clustering algorithm that we discussed, k means that is similar, right? So KNN and k means. So there we identified k value so by using a plot called elbow plot. That means so we have to give as a data scientist, you have to identify the best k value and you have to use that in the algorithm. Here also the KNN k has to be determined based on the various methods, right? So if you say k equal to 1, k equal to 1, that would become one nearest neighbor, one NN or one nearest neighbor algorithm. And what do you mean by one nearest? Okay. For example, we have a two class problem here. One is the pink color. This is a class one. Let's say, for example, accepted, and this is a rejected class. Now, these are feature space, feature one, and feature two. I have a new data point. A new data point for that we have feature one and feature two. I want to find out what is the class for that data point. Now, what we do is we will find out the distance from this data point to all the data points in the data set. And this new data point uh, is very near to this data point. That means when you find out the distance from this new data point to all the data points, so like this, the distance, okay, from here to here, find out all the data points like this. Then we found that the distance from this data point to the new data point is very, very low. That means this is very near. This is the nearest neighbor. When you say the distance is low, that means the neighbor or the nearest neighbor. So when you say k equal to 1, that would become one nearest neighbor. So in this case, I will find out the one nearest neighbor for my new data point. So in this one nearest neighbor, in this vicinity, I have one data point, and this data point class is accepted. Then I'll assign this accepted class to this new data point. That means the new data point class, so based on this one nearest neighbor algorithm, is accepted. So when you say k equal to 2, so when you say k equal to 2, so in this vicinity, okay, once you find out the distances from all the data points, find out which are the two nearest neighbors with this new data point. The two nearest neighbors are, one is the rejected class, one is from rejected class, the other is from accepted class. So in this case, there is a tie. Okay. So we cannot decide which class has to be given to the new data point. So in this case, what we do is again we'll fall back to the which is the most nearest out of these two data points. Out of these two data points belongs to different classes. So in this case, again, we'll say this data point is very near to the new data point. I'll take this data point class assigned to this. So that is in case of two nearest neighbors. Now coming to three nearest neighbors. So in this vicinity, I have three data points. So if you want to find out the most near to this new data point, so I can draw a circle like this. In this circle, in this vicinity, I have three data points which are very near to this new data point. And two are from this blue class, one is from pink class. And in this neighborhood, so which class has a majority? The blue class has a majority. So I'll assign this blue class to this new data point. Okay. So that's how based on in the neighborhood, the nearest neighborhood, which is the majority class, and that majority class we are going to assign to the new data point. If you talk about the 8 nearest neighbors, so then we have to assign the pink class to the new data points. That means based on the number of k value, so we are going to identify the k nearest neighbors for the new data set. Within that k nearest neighbor, So which is a majority class, that majority class would be assigned to the new data point. So that is a procedure we are going to follow for this k nearest neighbor. Okay, so let us understand this algorithm, KNN algorithm. So the first step is, yes, load the data, initialize k, that means k value, let us say for example k equal to 2 or k equal to 3 or whatever the value that is. Then for each example, let us say I have data points. So data point 1, 2, 3, 4, 5. Okay. And I have features like this, feature 1, feature 2 like this. Now, what we do is for each example in the data set, calculate the distance between the query example and the current example from the data set. I have a new data point, for example. My new data point is, let's say, X, and these are the feature values, feature 1, feature 2. Now what we do is for this new data point X, find the distance from this data point to X data point, from this data point to X. Let us say from here to here, the distance is 5, and this is 15, this is 200, and this is 2, and this is 9. And let us say this classes for this is class yes, okay, yes, this is no, okay, yes, and these also yes, for example. These are the class variable. So first we have to find out the distance from this new data point to all the data points that are there in the data set. What is the next one? So add the distance and index of the examples to an ordered collection. That means just sort these distances. Okay, that's fine. So we can sort these distances based on the ascending order. Then pick the first k entries from the sorted collection. Means when you say k equal to 3, okay, pick the top 3 after sorting, okay, in descending order, not ascending order. uh, Sorry, this is in ascending order only, so where the distance should be low, right? Yeah. So if I arrange this data in ascending order, this is a class. Okay, so let me write it here. This is a second class is y, then 5 class is y, then 9 class is y, then 15 class again y, 200 class is no. Okay. Now so this data has been ordered in ascending order. Then we have to pick the first k entries. What is the k value here? K equal to 3. Then pick first 3 entries from the list sorted collection. Then get the labels of the selected k items. So when you say the k items here, so just check the labels of these first k items. So the labels are y, y, y. Then I'll take this y, assign it to the new data point. So if it is a classification, if it is a regression problem, let's say for example, what I will do is we'll have the numerical values here in these 3 items, then take the mean of these 3 values. If it is numerical, then I'll assign that mean value to this new data point. So that's how the k nearest neighbor algorithm can you apply to the classification as well as regression. If it is a classification, I'll pick the top k values or the k nearest neighbor data points, check the labels for those things and assign the mode value for that, the majority class from that nearest neighborhood. If it is a regression problem, take the mean of all these values within the vicinity in the neighborhood, then assign that average value to the new data point. So that's how we are going to solve the classification as well as regression problem using k nearest neighbor. Right. So let us understand this example, this k nearest neighbor algorithm with a simple example. So I have a few data points, ingredients. Total we have 6 data points and 2 features. So feature 1 and feature 2. And this is my class variable. Okay, so this is my class variable. And sweetness and crunchiness of the ingredients, and we have food type. So how many classes are there? We have 3 classes: fruit, protein, and then vegetable. So these are the different classes, 3 classes we have. So when we visualize this data, So in a two-dimensional space, that is a feature space here, feature 1, feature 2. And so here you can see a pattern like vegetables, proteins, and fruits. So the fruits are basically, the sweetness is very high and the crunchiness varies from low to high. Okay, so there is a crunchiness that varies from low to high. And coming to these vegetables, the crunchiness, okay, this is a crunchiness, right? The crunchiness is high, but the sweetness varies from so low to high. These are low, these are high, and here low to high. For proteins, the sweetness is low as well as crunchiness is also low. Okay, so these are a clear pattern that we can identify here. And we have a problem. So that is a new data point, that is tomato. And now we have to classify this tomato into one of these classes. Then how do we classify this? We can classify this tomato into one of these classes if this tomato is very near to any of these data points. For example, so we will find out the distance from here to here for all the data points like this. Then based on the k value, k equal to 1, k equal to 3, 4, like that, based on these values, we are going to identify so which are all the nearest neighbors to this tomato, and we'll consider that class. So if you say k equal to 1, I'll consider which is the nearest neighbor from this tomato. If it is, let's say, for example, apple, then I'll assign this fruit class to this tomato. Let us say if this tomato is very near to, let's say, carrot, then I'll assign the carrot class is vegetable. This vegetable I'll assign it to the tomato. So like that, we are going to identify the distance. When you say nearest neighbor, how do you define the nearest neighbor? That is based on the distance only, right? We'll compute, we'll find out the distances from each and every data point to the new data point. Then we'll sort it out, sort the distances and find out the minimum distances based on the k value, and we'll consider those many data points while assigning the class. Yeah. So as we discussed, we are going to use the distance, and we know the distance is Euclidean distance. We're going to find out. To find out this Euclidean distance, we should have the features for tomato also. For the features of the tomato are sweetness is 6, crunchiness is 4. Now let me open Excel sheet. Let us find out the distances from all these data points to this tomato. Right, so here the same data set. Food type, okay, there is a class variable, and we have a new data point, tomato. So the features for the tomato is 6 and 4. Okay. The first step is find out the distances from this tomato to all these data points, all the data points. So how do we find out? Euclidean distance, that is the square root of, let us say, for example, let us find out the distance from tomato to apple. 6 minus 10 square plus 4 minus 9 square, that is square root again. Then the distance is 6.4. So 6.4 is the distance from apple to tomato. Likewise, find out the distances from all the data points to this tomato. Those distances are here. Then sort these distances, identify the distances from minimum low to high. 1.4 is the lowest distance, 3.6 is the next, then 5 is the next. Like that we can order these distances. Now based on the k value, k equal to 1, that would become 1 nn. So that would become 1 nn. So if you say 1 nn, what we have to do? The lowest distance, that means the nearest neighbor of one data point. The nearest neighbor, so that is basically 1.4, the lowest distance. So this is with carrot. So carrot is very near to this tomato. Then what is the class for this carrot? That is a vegetable. Then simply take this vegetable class and assign it to the tomato. So that is in case of 1nn. Then let us say, for example, k equal to 3nn. 3nn means find out the three nearest distances like this 1, 2, and 3. Then see these three distances are with which data points. So this is lady's finger, banana, and carrot. So these three, uh, the data points, the classes are vegetable, fruit, and vegetable. So out of these three, the majority class is vegetable. Then again assign this vegetable to the new data point. All right. And if you mention k equal to 2, so if you see k equal to 2, two data points are here, which are belongs to different classes. One is banana, the other one is carrot. So fruit and vegetable. So there is a tie actually here. So when you have a tie, so what you can do, again you can fall back to the k equal to 1, that is which is a very near to the new data point. So 1.4, that is vegetable. So that means, so the tomato belongs to vegetable. So that's how we can assign the class for a new data point based on the existing classes. Right. Now let me show you how do we implement this k nearest neighbor algorithm in the Python. And also we are going to see how do we identify the best k value for a given data set. So that is nothing but based on the grid search. Okay. So grid search, let me show you how do we apply the grid search and how do we identify the best k value for a given data set. Yeah. Right. So there is a k nearest neighbor classifier. We are going to implement in on a classification problem. So divide the data into x and y variables. And here we are going to apply again k-fold cross validation to find out the accuracy. Number of folds are 10 k-folds. And k nearest neighbor classifier n underscore neighbors are k value, k equal to 14. We'll discuss how we have identified this k equal to 14 in a moment. First, let me show you how do we build this algorithm and how do we find out k fold. This has to be executed. Right. So using this k nearest neighbor algorithm, so we have got the score of 75.64. Okay. Now coming to the point, how do we identify the best k value? So here we have given k equal to 14. How do we get to know that? So we have a methodology called grid search. So ideally, what we have to do is take a k value, k equal to 1, build the algorithm, okay, get the accuracy. Then k equal to 2, build the algorithm, get the accuracy. This accuracy 1 and this accuracy for k equal to 2, like that. So test, okay, as many k values as possible, get the accuracies and compare the accuracies, and for which k value the accuracy is more, then we can settle down with that k value. So if you see here, so there are infinite number of values, k values are possible. So are you going to manually do all these things? K equal to 1, k equal to 2, and build the algorithm like this. So one is k equal to 1, so k equal to 2, k equal to 3, and keep track of all these things. So literally we have to do like this, for example. So build k equal to 1 here first, 67%. Then go for k equal to 2, 71. K equal to 3. So like that you have to build actually, and you have to keep track of these accuracies every time. But this is a time consuming process, inefficient process. So for that, we have a methodology called grid search. What is this grid search? Within the space, okay, within the space, the range of values that you are going to assign for the k. So this grid search CV automatically builds all the algorithms for possible k values, what are the values that you have given, okay, and then it gives us the accuracy for us. Let me show you that. So this is the grid search CV. I'm going to test my model on this space, basically 1 to 40. We are going to build the models k equal to 1 to 40 and get the accuracies, and we are going to compare. So at what value of k the accuracy is more. So that is what we are going to do, and that we are outsourcing to the automation. That means we are not going to do manually, right? So we are asking the grid search cross validation automatically does that job. Right. So the values are k values are 1 to 40, and the best grid score is this. So at k equal to 14, the best score is 0.75 or 75%. Now let us visualize what are the accuracy values for each of these k values. So I can visualize that using this code. Yeah. So you can see here for each of the k value, what is the cross validation accuracy? So this k equal to 1, k equal to 2, like that, k equal to 3, 4. And so you can see at k equal to 14, this is where the highest accuracy. And then it drops down, then again it goes up, and then slowly it is dropping down. That means at k equal to 14, this is where actually we are getting the highest k, the accuracy value. Right? So then that is where actually we have used the k value, k equal to 14. So this automation of identifying the best k value in a KNN. So that is possible using grid search, and not only here. Okay, so for each of the models we have different hyperparameters, right? So if you talk about the decision tree, we have to identify the number of leaves, the maximum depth, okay? And these are the hyperparameters that you have to use. And for that also you can use this grid search CV. Okay, to identifying the hyperparameters automatically. So this methodology is the best methodologies. Methodology is only one methodology, the grid search CV method. Not only here, you can use it in. We will use it in neural networks, support vector machines, decision trees, or whatever the models that you can think of, where you have to fine tune the models. So everywhere you can use this grid search CV method. Right. Any questions? All right. Any other questions, guys, on this? Okay, nearest neighbor. Okay. So if none, then we will wind up the session for today. And Monday would be Monday. We are going to discuss about the neural networks. Okay. So that would be our last class. And also, I'm going to showcase. I'm going to show you how to build a best model or decent accurate model by considering a lot of other different models from starting to end. Okay, so that is what we are going to discuss on Monday, along with the neural network, and that would be our last session. So in the series of the machine learning and artificial intelligence. Right. So there are some questions in the boosting. Which one is a good? The best method is XGBoost. So if you want not only in a boosting method, if you want to build any algorithm, first try with the XGBoost. Go with the XGBoost, then go with the LGBoost, then other models you can try. Real-time implementation of the algorithm for diabetic problems. Okay, what are the parameters we need to collect? Yeah, the parameters. So little difficult for me to say because I'm not from the healthcare background, but you can think of actually. So the parameters based on the the human body measurements and health, medical health status. So those things you can consider. But again, so I cannot tell you accurately because I'm not from that background. What are the differences, okay, between KNN and K means? KNN is, yeah, K nearest neighbor is a machine learning algorithm that is a supervised learning algorithm. K means is a clustering algorithm which is unsupervised machine learning algorithm which is to find out the patterns in the data. Right? And K nearest neighbor algorithm is to predict our classification to classify, okay, a new data point into one of the existing classes. Okay, will there be more workshops? Yes, we are going to conduct yeah, more workshops actually on the deep learning, especially neural networks. That would be in the month of Jan. Okay, we'll let you know definitely. Yeah. Okay, so should we have to normalize and encode the attributes? All right, we have to exactly. So this is a good point. We have to normalize the data set when you are using especially the distance based methods like k nearest neighbors or clustering methods. Okay, so as we have seen in one of the clustering examples, when you have the data with a different scales, right? So the high scale or high ordered high magnitude column or feature would completely bias or dominate the entire analysis, right? So it is good to go for the normalization when you are using especially the distance based methods like k means the hierarchical or k nearest neighbors. Yes. So which machine learning tool will be used for the fraud detection? Upfront, we cannot tell actually. Okay, so which one would be used for a given context? See, as I said, the best accurate algorithm or a robust algorithm so far is XGBoost. Most of the times, I cannot say 100% of the times. Most of the times, you can try the XGBoost first. Then, if it is not giving you the good accuracy, then you can try other methods. Right. So, example for text classification. You can use for text classification the naive base algorithm. It works best basically on the text data. Okay, or support vector machines, or also I can use the neural networks. The examples are what you can think of. Let's say, for example, I can give you one a workflow. You can use that. So let's say, for example, I have a company and I'm offering some services or products, and the review. So reviews about this product or service, people are posting in a various social media platforms. Let us say Twitter, okay, or the online platforms such as Amazon or Flipkart or some other social media sites, Facebook and all those things. Now, as a product owner, okay, or a service owner, so I want to understand. So, what kind of comments the people are posting, our customers are posting, whether they are posting positive comments or negative comments. So, one way is what I can do is I can extract these reviews, or I have to go through each and every review, or I have to go through each and every tweet to understand whether they are positive about my service product or negative. So this is very a huge task, right? So if at all there are thousands of reviews, thousands of tweets or posts, so it is not feasible for us to go through each and every review and tweet manually. For that purpose, what we can do is I can extract the data from these platforms. The first step is clean the data, process the text data, pre-process. Then build the algorithm. You can think of the algorithm is So knife base or SVM, or you can also build the neural network based algorithms. Once you have the algorithm, then I can use this algorithm for all the new tweets. There's a new tweet, so the customer has posted. So your services are good, or the product is worst. Okay, worst service, or someone has posted the price is too much, the price is very high. So like this, these are the comments the people would post. What I would do is, so as soon as, so there is a tweet that appears with my product name, I'll pull that tweet, apply to the model. The model throws out positive or negative. So on a given day, let us say there are 10 positive reviews and there are 20 negative reviews. Then what I would do, so I'll take these 10 positive reviews and I'll ask my team to analyze, and I can understand. So for what service and what features the customers are happy. And there are negative 20 reviews, I'll send it to another team and I'll ask them to analyze, hey, why these customers are unhappy, what kind of the features these customers are, largely unhappy. When you're talking about a mobile phone, for example, so about the battery, they are very unhappy, or touch screen, or other some features, right, or sub products, why they are unhappy largely. Okay, I can ask them to analyze these 20 tweets, so I can understand the customer pulse. Okay, so these are the applications of the NLP or text mining. And also, not only positive or negative, so there are something called as emotions. We have humans would express 8 emotions. Whatever the statement that you make, whatever the statement that you write, so that statement or this expression, whatever you make, right, so those expressions we can assign 8 emotions, like happy, joy, disgust, okay, anticipation, trust, sad. Like that, we have total 8 emotions, and each and every post or every review, I can rate against these 8 emotions, so that I can understand in depth about the customer, the pulse. Okay, so these also is very very useful to understand the customer pulses when it comes to services and products. So these are the applications of NLP, and there are many other NLP applications are there, but this is one of the classic example, or the use case where most of the companies are implementing. Right. So there are a few more questions. For age and gender detection. Yeah. So again, we cannot say upfront. So which algorithm is best for a particular problem, right? So we have to try it out, different algorithms, and we have to find out which algorithm is going to be good for a given problem, right? So even for the optimization also. Yeah. So there's a question: if I'm doing a project on credit card fraud detection, what would be my objective? So the objective here, the question here is, if someone is doing a project on the credit card fraud detection, what would be the objective? Objective is, for a given data point, for a given transaction, the transaction is a fraud transaction or genuine transaction, right? So that is the objective. So it's a classification problem, and you can use any of the classification algorithms that we have discussed. So which ML algorithm is best for optimization? See, we are using optimization in ML algorithms. If you're talking about the neural networks, right? So there we are using a lot of optimization algorithms, gradient descent, right, in the ML algorithm. But I'm not sure other way around. Yeah. Okay. So there is another question. Make a workshop on LP text extraction soon. Definitely will plan for one. Yeah. So hybrid algorithms. So if you're talking about the semi-supervised algorithms, right? Uh, yeah, I hope that is what actually we're talking about, semi-supervised. So which is called as hybrid algorithms. So which is the combination of clustering plus the supervised learning algorithms. So these, yeah, semi-supervised algorithms will be used largely when you don't have the y variable in the data set. Okay, so that we can apply the clustering technique to find out the y variable. Then we'll apply uh, the algorithm. Let's say, for example, so I have a data set. I have a data set. This data set doesn't have any y variable. So I have x1, xn. But I want to use this data set for the classification problem or supervised problem. What we can do is I can apply unsupervised technique such as clustering, unsupervised learning techniques such as clustering. So once I apply clustering algorithm on this, so what we can expect is groups, right? Groups of data like this. Cluster 1, cluster 2, okay, cluster 1, 2, 3, 4, and 5. Then I'll use, okay, these values as labels. Okay, I have now labels here. So first few data points are 1, 1, second few data points are 2, 2. Okay, then 3, 4, 5 like that. So this I'll consider as a class. Then I would apply supervised algorithms, any classification problem on this. So this approach is called as semi-supervised approach. All right. So yesterday attendance link, right? So if you have not given, that is fine. Okay, one day doesn't make much difference. We are not going to, the judge or so we are not going to prevent the certification, right? So based on one day's attendance, so you don't have to worry about that. Okay, that's fine. So if you don't have to, if you are not, if you have not given the attendance yesterday, that's fine. Could you please take an example of hybrid algo with coding? Yeah, I'll have to check that. Okay. Probably I can discuss on Monday. So one example on this. Yeah, one more question. When engineering concepts, yeah, I'm not sure about that question. Okay, solid, guys. And if you don't have further questions, we will wind up the session for today, and we'll meet on Monday. And Monday would be our last session. Yeah. Thank you. Thank you very much.